In a unique demonstration of Galileo's famous experiment, Apollo 15 astronaut Dave Scott simultaneously dropped a hammer and a feather while standing on the surface of the moon. Have we seen this? Out of curiosity? Seen this video? Yeah. No? A couple of no's. All right, I'm going to show it to you after this. It's amazing. Okay. If the gravitational field strength of the moon is 1.6 newtons per kilogram, the hammer had a mass of 450 grams and it was dropped from a height of 1.4 meters. Calculate the speed of the hammer as it hit the moon's surface. Okay, so for something like this, remember that our change in gravitational energy is equal to our change in kinetic energy. Okay, whatever we lose in gravitational, we gain in kinetic. So if we put in our formulas, our change in gravitational energy is mg delta h. Our change in kinetic, since our mass isn't changing, it's 1/2 m change in velocity squared. Okay, so our velocity, it's starting from 0, so we probably don't need to change it, but we'll leave it there anyway. Okay. If we fiddle around with this equation a little bit, you'll see that the mass of the hammer hasn't changed, so we can actually cancel that out. And we get g delta h equals 1/2 v squared. We can rearrange this further. We're looking for the speed of the hammer. So we can do 2g, I should do change in h, 2g delta h. Oh, that's a terrible delta. I did, I got a new computer. 2g delta h, square root of that will be equal to our velocity. Happy with that? I've just multiplied both sides by 2 and then taken the square root. So let's do this. 2 times g, don't be fooled here, g is 1.6. The height is 1.4. Yep, that's what I get. 2.12 meters per second. Okay. Just for the thrill of the chase, should we do this another way and test that we're right? No? No, we're doing it another way. Okay. Why? Okay. You're right. Your opinion. I'm not listening to that. Okay. Let's do this in a different way with Subat. Okay. So let's consider this as a projectile falling downwards. Let's do our Subat equation. So we know our distance is 1.4. We know our acceleration is 1.6. And we know our initial velocity is 0. Happy with this so far? So if we work out v squared equals u squared plus 2as, u is 0. So v squared equals 2as, and you'll see that v square root of 2as, I'm not even going to bother calculating that because it's the same thing. Square root 2g is a, and the change in height is the distance traveled. Okay? Holds up regardless of how we do it. So you can do this with energy, or you can do it with Subat. Either of them would give you the correct answer. The one the book uses as an example here is energy, because that's what we're looking at the moment, mechanical energy, but just showing you that you can do it either way and you'll still get the right answer. All right, I'm going to find this YouTube video. Have a go at the next one.